Hi everyone, I hope all of you are doing well. Welcome, thank you for tuning in. So, as I'm sure you guys can see on screen, the title of this talk is Evolutionary Engineering, Optimizing Software Projects with Genetic Algorithms. So, what do all of these complicated words mean? We'll find out very soon, but for now let me tell you a bit about myself. My name is Rahul, and I am a software engineer here at BBD. As part of my job, I work with full stack web development, and I'm currently working in logistics management. I'm also fortunate enough to do a couple of other things on the side as well. I help some of my friends and colleagues, and I do some volunteer work whenever I can. I studied computer science at the University of Pretoria, also known as Tux, and trust me when I say they did not mess around. It was difficult, but I'm really happy with the path that I took and the career that I chose. So growing up, I've always enjoyed optimization problems, and I've always enjoyed solving problems in general. As I'm sure a lot of you guys know, in computer science, there are a lot of problems that we have to solve, especially in the software engineering domain. I've always loved thinking outside the box, and I'm grateful that the line of work I'm in certainly indulges this idea. As computer scientists and software engineers, or anyone in the tech space, we always find really cool and innovative ways to approach some really difficult problems. I love the fact that we're not afraid to reinvent the wheel, even if we end up confusing everyone else around us. I think it goes without saying that I also really enjoy programming. This was apparent all the way back in high school when I first started writing code. I love the fact that you can write code to do almost anything, and I particularly enjoy looking at different styles of programming that we can apply to various problem domains. It gets a little bit stressful sometimes, but I'm still really glad that I give it a try, and I'm really glad that it's what I do. During my undergrad years in university, I realized that I really enjoyed solving optimization problems. These are problems where you have a bunch of different variables, and you have to find the best values for all of these variables, such that your solution is the best possible solution it can be. So how do we visualize this? Let's imagine we have a massive project that we have to get done. We start off by planning it, and when we plan it, we just realize we have a certain amount of time we can spend, we have a certain amount of money we can spend. Our project may have a certain number of phases and a certain number of requirements. So we may draft a project plan, and over a couple of days or even a couple of weeks, if we have a really large project, we're going to make some changes to this such that we know exactly what to do and when to do it. So you may come up with a draft of a plan, and you may realize, hey, this is not quite right. Maybe I need to make a phase or increase the duration of a phase such that it's a bit longer. I may realize that one of my phases aren't really required, but they're more of a nice to have. Or, as I'm sure a lot of you know, I may need to give the team even a bit more work. This is an optimization problem. And what I love about this is, what if we took code and programming and applied programming to solve this problem, essentially automating it for us? That's something I fell in love with while I was studying, and I thought it would be such a cool thing to do. This interest led me down a rabbit hole of research, and it ended up in me studying further in university, as I studied my honors as well as my master's in computer science at Tux, and I focused my research on using machine learning to solve these kind of optimization problems. In particular, I looked at a special area of machine learning known as genetic algorithms, and I used these to solve optimization problems. And this is why today I'm going to be sharing this knowledge with all of you. So what is a genetic algorithm? We'll dive into a full definition a bit later, but essentially a genetic algorithm is a programming technique that draws inspiration from the history of humanity. It looks at where we started, and it looks at the steps we took to get to where we are today, and it applies this in the realm of code. I really enjoy this technique, and I know that it has the potential to benefit each and every one of you watching today. So I really think you should care about it, and I think you can definitely find a way to integrate this technique into a lot of your projects. With the rise of neural networks, and large language models in particular, I feel like this technique has slipped under the radar, especially with big tech giants basically shoving LLMs into our face. I think there are a lot of cool alternatives to approach some of our daily problems. GAs, I think, are incredibly powerful when used correctly and used in the right scenarios. So, like I said, we'll dive into a full definition shortly, but in essence, yes, GAs will optimize something over a certain period of time. It's just like how, as humans, we evolved over a certain period of time. Yes, think of it as survival of the fittest, but in the realm of code. So we know that GAs draw inspiration from humanity and evolution, but what aspects exactly? And to find this out, we're going to spend a few minutes talking about evolution. So I'm sure you guys have all seen this famous image at some point in your lives. Yes, it's the classic illustration of human evolution. It looks at how we started as primitive apes and how we evolved to modern day humans, or basically apes with less hair. So I'm not a history expert by any means, so I'm not going to delve completely and give you all the nitty-gritty about evolution, but we're going to touch on the relevant concepts. I'm sure most of you have heard of Charles Darwin. He's the man who came up with the theory of evolution, and this theory remains as one of the most plausible theories of how we came to be who we are today. So if we go back to this image, how long do you think it took us to get from here all the way to there? So when I first looked at this, I guessed around a couple 100,000 years. It felt about right. I asked a few people and they guessed the same. And I was shocked to realize that it actually took around 7 million years for us to transform from primitive beings, apes, to the modern day humans that we are today. If we put that number into perspective, an average human life lasts around 80 years. Yes, so it took around 87,500 human lifetimes for us to just transform to the beings we are today. And what we learn from this is that evolution in a nutshell is about these small incremental changes over a very long period of time. Small steps which result in drastic change when you compare the starting point to the finish point. And it's this concept of iteration over a very long time that we harness is when we write genetic algorithms. So we know roughly what evolution is, but now we need to figure out how it works. So what I'm going to do now is I'm going to guide you guys through a few evolutionary concepts that we use when we write GAs. So firstly, most of us will argue that we haven't just changed in the past 7 million years, we've actually changed for the better. But I never know, maybe you're a massive Planet of the Apes fan, but regardless, most of us would agree we have improved. But how have we improved? How is this an upward trend? And this is where the concept of survival of the fittest comes into play. But how does that work exactly? So let's say you have a massive group of people. These can be humans, they can be apes, whatever you want. But let's say that they're human beings. This massive group of people, they have a name. They're called a population. Now, all members of our population have certain traits which make us better or worse at certain things. That's what you mean. And they make us who we are. They could be related to our physical, mental, or behavioral abilities. And these are all hard-coded into our DNA. And a combination of these traits could either result in us performing better than someone or worse than someone else. For example, someone who has long legs and someone who's a bit stronger than other people, they're going to be faster at running. And if their legs are longer than everyone else in the population, they will be the fastest runner. Now, what we can do is we can take everyone in our population and we can actually find a way to quantify these traits and basically give them a score which tells them how good they are overall at a certain thing. And we can call this a fitness score. For example, someone who's a faster runner than another person will have a higher fitness score than them. Or someone who's a better programmer than another person will have a higher fitness score than them. is now the more desirable the traits, the more desirable the fitness. And it's thus perceived that a higher fitness is usually better than a lower fitness. And this is why people with higher fitness are perceived to be better candidates for reproduction. And this is why when people have children, yes, the children will inherit their traits and on and on and on, and generally you have more fit individuals in a population. So when two humans reproduce, there is an intermingling or combination of DNA, and this is what leads to offspring. So what happens during reproduction? Well, that's a question for the parents. But what happens after reproduction is you have offspring. And what happens when you have parents and offspring together? You have a family. So what we're going to do now is we're going to examine a family, yes, and we're going to look at some other traits that could be inherited after reproduction. But let's change the family. Let's look at a family with fewer issues. Much better. So if we look at this family, yes, we have two parents and we have three children. Yes, if we look at mom's hair, yes, it is curly, yes, and if we look at dad's hair, yes, his hair is straight. But notice how the two sons have curly hair, but the daughter has straight hair. So what's happened here is we've seen traits get inherited to offspring, but we've kind of seen an interchange of traits, like the sons got the mom's trait, yes, the daughter got the dad's trait. So what happened here is that during reproduction, there was some intermingling of DNA. Yes, and this phenomenon actually has a name, yes, it's called crossover. So let's look at another family now. Yes, over here we have two parents, yes, and we have two children. Yes, if we look at mom, dad, and the son, they all have the same color hair, it's brown. But if we look at the daughter's hair, yes, so her hair is blonde. So how does the daughter have blonde hair but the parents have brown hair? Well, there are a couple of explanations for this. Yes, the first one is that mom probably wasn't very honest with dad. But the more likely explanation is that during reproduction there was some unwanted or unintentional modification made to the DNA which resulted in a different trait. And this is called mutation. So, like I said, yes, we have parents, we have children. Yes, these children are going to meet other children. Yes, they're going to have children as well. And this is going to go on and on and on. Yes, the children's fitness are going to be some kind of relation to the parents' fitness. Yes, and their children will also have a fitness. And yes, what's going to happen is that over many, many, many years, we're going to get children having children, having children, having children, and this process is going to repeat itself. Yes, and these repetitions are referred to as generations. And it is with these generations which transform us from primitive beings, little apes, to these massive populations of human beings that we are in the modern day. So let's recap a little bit. Yes, we started with a population. Yes, we saw that yes, each element or each individual in our population can have a fitness score. Yes, after reproduction, we saw that crossovers or mutations can occur when having children. Yes, and we saw that this process can repeat over many, many generations. And this, in a nutshell, is evolution. Obviously, it's not everything, but it is the concepts that we need to understand for genetic algorithms. So Darwin came up with this theory, and in the 1960s or so, a man by the name of John Holland, he looked at Darwin's work and he realized, wait, I can code this, or I can take these concepts and I can use them in my code. And this is how genetic algorithms came about. So now it's time to look at a bit more of a formal definition. So GAs are inspired by the process of evolution and natural selection. They mimic the principles of biological evolution to solve optimization and search problems. Yes, they begin by generating a population of solutions. Yes, they take these solutions and they evaluate the fitness. Yes, they reproduce them using mutation and crossover. Yes, and this process gets repeated over many generations. And that is a GA. Yes, GAs are designed to tackle optimization problems. Yes, optimization problems, as like I said, are where we seek to find the best solution from a set of possible solutions by using variables and finding the best values for those variables. Think of it as finding the most efficient route for a delivery truck. or the optimal design for an airplane wing, yes, or yes, the best project plan is for a project. And these problems occur everywhere in our personal and professional lives. GAs excel at solving these problems because they explore a wide range of possible solutions and iteratively improve upon them over time. So now it's time to break down the GA to see exactly how they work. And to do this, we're going to go back to my example of project plans. And we're going to use a genetic algorithm to optimize this project plan. So before we start, like I said, optimization is about finding the best values of variables. If you think of humans, yes, and we consider optimization, we may want to find the fastest runner. So we look at their running speed, for example. In terms of a non-organic item like a project plan, what are we going to look like? What are we going to look at, rather? It's not as straightforward. But like I said earlier, we want our project to last the shortest amount of time. We also want it to cost the least amount of money. So let's look at time and cost. These can be our variables. Now that we have something like a project plan, if you remember, we start with a population. How do we create a population of project plans? Sounds a bit weird, right? Well, it's quite simple. In terms of coding, all we're going to do is randomly generate some project plans. And we're going to define some rules in our program such that the duration of our project can be between a minimum and maximum threshold that we set, such that we have some control and we still get a variety of different elements in our population. Yes, these project plans will consist of various phases and various features. Yes, and then we have our population. Now, after our population, we have to evaluate fitness. But how do we evaluate the fitness of a project plan? As with humans, it was easier, just because things like running speed and personality make sense to us. But how do we do this with something intangible? Well, we have time and cost from earlier. So yes, let's look at the time and let's look at the cost. And let's think, how do we come up with a single quantifiable way to look at this project plan and say, this is how fit it is? So in order to do this, I'm going to use the variables I have. And what I can do is I can take the product of my cost and my time. This is going to give me one numerical value. And because we're trying to minimize the cost and the time, the smaller this value, the better the fitness. This would work very well. But when I write this code, when I work with GAs, I like seeing bigger values of fitness to interpret as better. I want a higher value to mean a higher fitness. In this sense, a lower value will mean a better fitness. So how can I correct this? What I'm going to do is, I'm just going to say 1 divided by the product of cost and time. This is going to give me a numeric value, and the larger this value becomes, the fitter the individual is going to be. Using this, we can calculate the fitness. And when we have this, we can figure out which element in our population is the fittest. And from there, we can select the fittest elements and we can do a bunch of other things. So this equation is 1 over cost multiplied by time is going to be specific to our scenario, our project plans. For a different interpretation of a GA, we may have different variables. We may come up with a different equation. These are different for every problem. We call this equation a fitness function. And this is how we use a fitness function to perform fitness evaluation. So now that we have fitness in our population, we have to start with reproduction. But we don't just reproduce every element. We want the fittest elements, or at least we want some of the fittest elements. So what we're going to do is we're going to select a random subset of our population. If we have 20, we'll select a random 5. And of those 5, we're going to calculate the fitness. And we're going to choose maybe the 2 or 3 fittest individuals to perform reproduction. And we're going to repeat this process until we have enough elements to carry on to the next generation. How do we do crossover? So when we reproduce, we can either have mutation or crossover. Let's figure out how we do crossover. It made sense in the concept of humans. We had the hair color and we had the hair type. How do we do this with a project plan? It's actually not that difficult. What we're going to do is we're going to pick a random point. Could be the one on screen, could be here, could even be there. but we're going to focus on the first point. And what I've done is here, I've just chosen a random point in 2 different project plans. In this case, it was the first phase. Right? And if you remember, crossover involves an intermingling of DNA or a swapping of traits between 2 individuals to create offspring. So all we're going to do here is we're going to change the traits. So we're going to interchange then between both project plans, and then we have our children to pass on to a new generation. And that's crossover. How do we mutate? How do we mutate? Well, it's quite simple. Yes, just like we did with crossover, we picked a point and we made some kind of modification. Now, mutation entails making some kind of a random or unintended modification. So we're going to pick a point. Let's pick a point denoted by the star. And then we're going to just make some kind of change. In this case, I increase the duration of the phase at that point. Yes, and I've successfully performed mutation. Yes, and that's my GA. Yes, I've had my population, I calculated my fitness, and I did my reproduction. Yes. And then after crossover and mutation, I repeated this over many generations, yes, and I will have an optimal solution at the end of my algorithm. So yes, now that we've seen how a GA works, yes, and we've looked at a bit of a theoretical example, let's put this in practice. So what I want to do now is take you guys through a little program that I made to demonstrate the genetic algorithm. But before we get there, let's cover some technical details. So I wrote this algorithm in Python. I wrote a front end using Angular, which uses the Python genetic algorithm, allows me to input some data. And the goal of this is to optimize the project plan. So what project plan? Let's create some sample data. So I have a little mock project here. As you can see, the name of it is a system redesign. It has a budget of $4,200. It has a duration of 32 weeks or 8 months. And it has different phases: planning, design, development, testing, and deployment. And as part of each phase, I can also have different features. So as part of planning, for example, I have requirements analysis and stakeholder meetings. Yes, for each of these features, I have a duration. I have an amount per hour that we would charge. Yes, I can also indicate whether I really need this or don't. Sometimes certain things are not that required. They're more of a nice to have because we may not have enough money or time. Yes, I can also indicate a priority of each feature, and I've done this for each phase of the project, as you can see, for design, development, testing, and deployment. Yes, that's our sample data. Yes, we don't need to worry too much about the exact values, but we need to know we have this for our program. Yes, and let's take a look at a bit of the code. So yes, here is a function that creates an individual of the population, yes, and then creates the whole population. Yes, as you can see, we take the duration and hourly rate for each feature, yes, we calculate costs, and we can randomize this slightly between a fixed minimum and maximum, yes, just for a bit of randomness and variation. Yes, and then for a predefined size, we will create our population. Yes, how do we calculate fitness? Well, what we do is we pick a project plan, yes, we look at the duration, we look at the cost, yes, we calculate the total time and total cost of this project, we compare it to our initial budget and time goals. Yes, if it meets these goals or if it improves, we give it a high fitness. If it doesn't, yes, we give it a penalty and we reduce its fitness. How do we do crossover? Just like in our example, is we pick 2 elements in our population, we pick a crossover point, and we interchange the information between the 2. What about mutation? Same as before, is we pick an element, we pick a mutation point, and in this case, what I'm going to do is I'm going to randomly increase or decrease the duration of a feature. Or if a feature is not required, I may delete it, or I may bring it back. That's an example of mutation. Then what we do is we put all of this together, where we take our population, yes, for a number of generations that we define. Yes, we select, calculate fitness, we perform mutation and crossover to reproduce, and we repeat. So now that we've looked at a bit of the code, let's actually go hands-on and give it a try. So here we are on our little program, that's like I discussed just recently, to optimize our project. So if we look on screen, we can see our sample data that's been input into the program. We have our project name, our budget, start and end date, phases, and then we have all of the features, as you guys can see over here. So what we're going to do is we're going to click submit, and then we're going to see our results. And this is our optimized project plan. Okay? So a couple of things to note here is if we look at the total cost and the duration, is these are actually lower than what we initially asked for. And that shows the GA's power in optimizing our plan. So as we have a lower cost, we have a lower duration, and what I actually did with the sample data is if you add up all of these weeks for each of the phases, it actually adds up to 37 weeks and not 32. So I've actually given this algorithm more data, and I've given it unreasonable data because yes, the actual amount of time is more than what I want it to be. And this shows the GA's power in actually optimizing it for us, because it's actually given us a project plan within our constraints. And how has it done this? So if we look at our first phase, we can take a look at duration, and we can see 2.93 weeks is not quite what we gave it as input. We actually gave it 3 weeks. So it's done a little bit of modification. It's decreased it a little bit, which means the cost of it has decreased. And this is what you would do in practice. If you realize, hey, we don't have enough money, let's reduce this by 2 days or something. So it's basically doing what we would do. It's automating it. If we notice as well, we have something grayed out here. This is a feature that's not required. Stakeholder meetings. And you can see what's happened here is that it said, okay, it's not required. We don't have the money, so we're going to leave it out. But it hasn't done this with every non-required feature. If we go down to testing, we can actually see that unit testing is still in our project plan, but integration testing has been omitted. So this is how we can see the power of our GA. It's going to try keep whatever it can keep in, but if it can't, it's going to omit something. And this is exactly what we would have done when we in our planning phase. And instead of taking a week, it took us about 2 minutes. So this is the power of a GA. And I think it's a really cool little program. Now that we've looked at a GA, we looked at some theory, we looked at a hands-on example, I don't only want to leave you guys with one example. So now what we're going to do is I'm going to discuss a couple of other use cases of GAs that hopefully spark your interest to build something and implement in your personal projects. So the first area we can use GAs in is testing. And in software engineering, we know that automated testing is a bit tedious, but it's very crucial for ensuring code quality and functionality. So GAs can be used to generate test cases that cover a wide range of scenarios, including edge cases that we may miss as humans. So what we can do is we can evolve these test cases through mutation, crossover, and come up with the best ones for our system. And this allows us to reduce bugs and make our software more reliable. Another great application of GAs is code optimization. So developers often need to optimize code for performance or make sure it reduces execution time such that we minimize memory usage or we improve efficiency in many areas. So what a GA can do is you can define a configuration for your code, and a GA can evolve your configuration and search through different ones, iteratively improve them and give you the best configuration for your program. And make sure your code executes the fastest, it takes the least amount of memory, and ultimately you're getting the best performance out of your code. Another area which I think is really cool is you can use a genetic algorithm to evolve features for machine learning models. So imagine a neural network. You have a certain number of layers, you have a number of nodes in a layer, you have learning rates, etc. So you can use a genetic algorithm to take this configuration and evolve it over time. And you calculate fitness by training your model, getting your accuracy or your recall, whatever you want, and you use that to penalize or increase fitness. And that way you're iteratively going to get a better model over time without you having to do any of the work. Beyond just optimizing a project, you can actually use a GA for CPU scheduling and batch processing. You can also use it for allocating resources in a cloud computing environment or organizing shifts. A GA can find the optimal solution that balance competing demands and constraints. For example, in cloud computing, is we can optimize the allocation of virtual machines for tasks. Yes, and doing this will allow us to minimize cost and maximize performance. So, another thing is that as software systems grow and expand, maintaining and updating them becomes very difficult. And over time, we get this thing we all hate to hear. We get something called technical debt. Yes, and what you can use a GA over here is that you can actually automate parts of your software maintenance process. Yes, they can be used to refactor legacy code. You can migrate code to new platforms, or you can even evolve a software architecture to adapt to challenging requirements and changing requirements. And by doing this, you can actually minimize or even eliminate technical debt and make sure that your software is always up to standard. Now, I've given you guys a lot of software-related examples, but it's worth noting that GAs go well beyond just software. Yes, we can use a GA in finance to optimize your investing portfolio. You can use it in bioinformatics for sequence alignment. There's logistics for route planning. Yes, and even in fields like music, you can use them for music composition or generating art, which I think is really cool. Okay, we've spoken about a lot today. So let me do a bit of a recap. Yes, we spoke about evolution. We saw how it works. Yes, well, at least the relevant parts. We took those concepts, we applied them to a genetic algorithm, we looked at a little example. Yes, afterwards, I demoed a little bit of a program where we saw how they worked in action, and then we looked at some other cool use cases of these algorithms as well. So the versatility of GAs make them a powerful programming technique to solve many different problems. And by leveraging and unlocking this technique, you can understand so many new things in your work. You can find new solutions to existing problems. You can come up with some really cool programs that could improve a lot of things. No matter where you are, you could be in software, you could be in finance, you could even be in music. So now that we've seen this, we've seen how they work, I want to pose a question to all of you. What are you going to build? What can you create with what I've taught you today, or what you've learned today, or what can you create with any new technique you've been looking at? So what I love about programming is that it opens up endless possibilities where you can create almost anything. Yes, and all of you watching have the power to create something. You could be the person who builds the next big thing. So I encourage all of you watching, just think about what you can build. Just, think about how can I use what I learned today, or how can I use something I've been looking at, or how can I overcome my procrastination by actually trying something I've wanted to try. You may just end up surprising yourself. You never know until you try. I hope that you all enjoyed looking at a very innovative and really cool programming technique today. And I hope that this sparks your interest to build something amazing. Thank you very much for watching. I really appreciate it. And I hope all of you enjoyed.